Hello students, welcome to Vastiversity. Today we're going to be doing linear programming. So, in many applications in business and economics and mathematics and physics, it's a lot of involvement in processes called optimization, right? In which essentially we're trying to find the minimum or maximum value of a quantity that we are interested in. So, a two-dimensional linear programming problem consists of a linear objective function, right? So we're going to call it an objective function, right? So objective function, right, can be written as z is equal to a times x plus b times y, where a and b are constants. And we would be given some kind of constraints, right? Constraints on x, constraints on y, or constraints on z. And so the objection essentially function gives us the quantity to be maximized or minimized, and the constraints determine the set of feasible solutions. Right. A lot of times people use like Excel, right? Excel is really great to do the objective functions and to do linear programming to maximize, minimize some values. Right? That's why Excel is a very popular tool to use. So when you are drawing your objection functions and the constraints, right, we're gonna get a feasible solution zone. Right. So essentially, based on all of the constraints, as we can draw them through the linear system of inequalities, right, as we did in the last lesson, we're gonna get the feasible solution area. Right. So feasible solution area, it consists of constraints and our objection functions. Right. So the constraint is going to tell us the feasible solution area. So in this area, we're going to have our optimized solution, right, the maximum or minimum in this somewhere area. So for linear programming. Right, for linear programming, we're going to have our first, essentially, a theorem of a linear programming is that if a linear programming problem has an optimal solution, so if we're saying that we do know that there is a maximum or a minimum, then it must occur at the vertex of the set of feasible solutions. So it must occur at a vertex. Right, so what are the vertices here? It's this point, this point, this point, this point, this point, or this point. Okay, so we have to consider those points in order for us to find the optimal solution. Okay, so what would be the process of how would we even find the optimal solution? So let's talk about it. So the first step one, of course, is for us to be able to sketch the region corresponding to the system of constraints. So we would be given some linear inequalities, right? Inequalities that would make the constraints. So these points would form the feasible solution. So it would be the points inside or on the boundary of the region we called feasible solution. So then we would have to mathematically or algebraically solve those linear equations or inequalities to find the vertices of that regions that we formed. And then we would be evaluating the objective function. So we would be plugging in that vertex point because we would get an x value and y value. So if we take a look at the feasible region, each point here has a pair of x comma y. Right, so we would say this one's x1 comma y1 type of thing. Right, so we would plug that into the objection function, which is z of ax plus by, and evaluate it, right? So essentially we would quote-unquote optimize the objection function. So for a bounded region, both a minimum and maximum value will exist. For unbounded region, if an optimal solution exists, then it will occur at the vertex, right? Because we did last time in the lesson, we did some inequalities that were unbounded, right? So we would have to really be careful with the boundaries. Okay, so let's go ahead and take a look at a problem. So problem example one. Right, let's take a look at example one. So we want to go ahead and find the maximum. Find the maximum value of z equals to 3x plus 2y. Okay, and then we're given some constraints, right? Constraints. That would be, so x must be greater or equal to 0, y must be greater or equal to 0, then x plus 2y is less than or equal to 4, and then x minus y must be less than or equal to 1. Okay, so this is all of our constraints. So the first thing, what are we going to do? We got to graph all of our constraints here, right? We got to graph them. So if we graph all of them, we're going to end up with the following figure. Okay, so if we graph all of our constraints, we're going to have this figure right here, right on the xy coordinate system. So here's our constraints. So we have x plus 2, y is equal to 4, right? But we're less than that, so we're going to be below this line. Then we have to make sure that x and y are positive. right? And then we have x minus y is equal to 1 is going to be this line. So that region is in blue right here. Okay, so now what do we have to do is, well, of course, we have to find the intersections and we have to find these vertices points, right? So to find the point 2, 1, we had to equate. We have to equate this one and this equation, right? Because that's where we intersect, and it's going to be this point right here. And then to find this point, we had to intersect this and this right together, so we would end up getting this point. And then at 0, 0 was the easy one. And then here, we'd have to do this too to get this point. Okay? So once we found all of the points, once we found them, we have to evaluate our feasible function. So our objection function at the feasible solutions. So at first point, at 0, 0, what are we going to have? We're going to have z is equal to 3 times 0 plus 2 times 0, which is equal to 0. Okay, at the second point, 0, 2, right? We're going to go upwards. So we're going to have z is equal to 3 times 0 plus 2 times 2, which is equal to 4. How about at the next point, right? So our next point is, so here's 4. So at point 2, 1, what are we going to have? We're going to have z is equal to 3 times 2 plus 2 times 1, which is going to be equal to 8. And then at the last point, which is at point 1, 0, we're going to have z is equal to 3 times 1 plus 2 times 0, which is equal to 3. Okay, so where is the maximum value occurs? So the maximum of z is at the point 2, 1. Right? So at this point right here in red, this is going to be our maximum. Right? This is our maximum for z. Right? So we were able to optimize and find the solution. Okay, and of course, we could try to find the interior points, right? We can try the interior points, but we will find out if we try some of the interior points, right? And let's actually do that. Let's actually try to find and see that there's no bigger points, there's no bigger value than the one we just found. So if we say, well, at point 1, 1, we're going to have that z is equal to 3 times 1 plus 2 times 1, which is equal to 5. Right, then at a point, let's say 1/2 and 3/2, we're going to have z is equal to 3 times 1/2 plus 2 times 3/2, and that will give us 9/2. Okay, and then if we try to do at the point, that's the last point, which is going to be 3/2, 1. So we're going to have z is equal to 3 times 3/2 plus 2 times 1 is equal to 13/2, which is still all less than 8. This is less than 8, less than 8, less than 8. Right, so 8 is the biggest value. Right? Perfect. So now we can also let's do another problem. Right, let's do example 2. So now, for example 2, we want to find the minimum value. Find the minimum value of the following function. So it's going to be z is equal to 5x plus 7y. Okay, and we are going to have the following constraints, right? So constraints are as following. We're going to have x greater or equal to 0, y greater or equal to 0. Then we're going to have 2x plus 3y is greater or equal to 6. Then 3x minus y is less than or equal to 15. Then negative x plus y is less than or equal to 4. And then the last constraint is going to be 2x plus 5y is less than or equal to 27. So try it on your own. Try to draw this constraining area and try to find the points. Okay? So after you find the points, you should get the following graph. So we will have this graph of the constraint region. So we have each of the solutions here, right? As we go through each of the lines, and we're going to have those points. So, okay, now we can have the biggest, let's see. So we have a lot of points here, so I'm not going to be labeling the equations, but I'm going to say that, okay, well, if we equate those equations and we try to find the region. So one of the easy ways to do it via tools, right? If you don't do it by hand, if you do it via tools, you can use Desmos. Desmos will draw a very nice picture of this constrained region. So now we have all of the corner points, right? All of the vertices. So now we have to evaluate at each point. So at point 0, 2, what are we going to have? We're going to have z is equal to 5 times 0 plus 7 times 2, which is equal to 14. Okay, then at point 0, 4, we're going to have z is equal to 5 times 0 plus 7 times 4, which is equal to 28. And then at the point 1, 5, we will have z is equal to 5 times 1 plus 7 times 5 is equal to 40. Then at the point 6, 3, we're going to have z is equal to 5 times 6 plus 7 times 3, which is equal to 51. Then at the point 5, 0, we will have that z is equal to 5 times 5 plus 7 times 0, which is equal to 25. And at the point 3, 0, we will have that z is equal to 5 times 3 plus 7 times 0, which is equal to 15. So clearly, right, this is going to be our minimum, right? And this is going to be our maximum. So here, actually, I'm going to change the color of it. So because we're going to be having only the minimum we are interested in. So for maximum, I'm going to make it, it's going to be maximum. So, okay, minimum is the point 0, 2, right? At 0, 2, this is our minimum. And then our maximum is 6, 3. Right, this is our maximum, this is our minimum. All right, perfect. So now let's go ahead and do one more unbounded region. Okay, let's do an unbounded. We have 2 examples for bounded regions. Now let's do an example for unbounded region. So example 3. So we still want to find a maximum this time, right? Find the maximum value of z is equal to 4x plus 2y. Okay, and our constraints are going to be as following. Okay, so we're going to have x again greater or equal to 0, y is greater or equal to 0, x plus 2y is greater or equal to 4, 3x plus y is greater or equal to 7, and negative x plus 2y is less than or equal to 7. Right, this is all of our constraints. So try to draw it by yourself. Try to draw it and show where the region is at. Okay, so after you've done that, you should be able to get the following graph, right? The following unbounded region, right? So this region is unbounded, right? There is no bonds to it, so it goes to infinity to the right, or positive infinity to the right, positive infinity up. So there is no bonds on this side. Okay, so what does that mean? That means we only have the solution, right? Since it's unbounded, we only have the solution at the region. So we want to find the maximum value. Can we actually do that? No, we cannot find the maximum value. Why? Because, well, we can put a 0.5 or a point eventually a point like 100 will be in there. So if we put 100, it's going to be growing infinitely big, right? Because this region is infinitely big. So we will be able to find a bigger point every single time. However, we are going to be able to minimize this, right? Let's see if we can find a minimum, right? Instead. So if you want to find, so we're going to say can't find maximum, right? Because the region is unbounded here, and it's growing to positive, bigger values every time. So let's go ahead and find minimum. So we know that at point 1, 4, what are we going to have? We're going to have that z is equal to 4 times 1 plus 2 times 4, which is equal to 12, right? Then at point 2, 1, we're going to have that z is equal to 4 times 2 plus 2 times 1, which is equal to 10. And then at the last point, which is 4, 0, we're going to have z is equal to 4 times 4 plus 2 times 0, which is equal to 16. So our minimum here is this value. So this is minimum, right? It occurs at point 2, 1. So here is going to be the minimum value. And we do not have any maximum values here. All right, perfect. So Now, let's take a look at a problem, right? At a problem here. So, like an actual physical problem. So, let's take a look at this one. So, we're gonna have an optimal problem, an optimal profit problem. So here is the problem. So a candy manufacturer wants to maximize the combined profit for two types of boxed chocolates. A box chocolate covered creams yields a profit of $1.5 per box, and a box of chocolate covered nuts yields a profit of $2 per box. Market tests and available resources indicate the following constraints. The combined production level must not exceed 1,200 boxes per month. The demand for chocolate covered nuts is no more than half the demand for the chocolate covered creams. And the production level for chocolate-covered creams must be less than or equal to 600 boxes plus 3 times the production level for the chocolate-covered nuts. What is the maximum monthly profit? How many boxes of each type are produced per month to yield the maximum profit? Okay, so what do we know? We know that our objection function is as following, right? We're going to have that combined profit. What's going to be our combined profit? Is going to be, so x, so let's say it's going to be what? 1.5x plus 2y, right? What is x in this case? X is going to be the number of boxes of chocolate covered creams, okay? And then y is going to be the number of boxes of chocolate covered nuts. Okay. So we have a total profit function here, which is 1/2 x plus 2y. So depending how many boxes we need to sell. Okay, but the most important part here is our constraints. So the constraints tell us, right? Constraints tell us that x plus y must not exceed 1,200. Then we know that y must be less than 1/2 of x. Right? And we know that x is less than or equal to 600 plus 3 times y. Okay, so we can essentially simplify it as the regular way. So x plus y is less than or equal to 1,200 minus x plus 2y is less than or equal to 0, and x minus 3y is less than or equal to 600. And of course, we're also assuming that, you know, we cannot have negative boxes, so we can have x to be greater or equal to 0, y to be greater or equal to 0. Right, this is also important. So this is our constraints and this is our problem, right? This is our problem. So pause the video to actually try to graph it and see what's going to be the region. Okay, so after you graph it, you should be able to end up with the following graph. Okay, so let's take a look at it. So here it is. Right, here is our graph. It includes the maximum monthly profit, the box of chocolate covered nuts versus the boxes of chocolate covered creams. Right, so we get the following constraints, right? The following points, the following vertices. So now we have to evaluate at each of the vertex. So we know, so at 0, 0, we're going to have that the profit is equal to 1.5 times 0 plus 2 times 0, which is equal to 0. Makes sense, right? At 0, 0, we have no profit if we don't sell any boxes. Then at 800, 400, we're going to get that profit is equal to 1.5 times 800 plus 2 times 400, which is equal to 2,000. Okay, but then at the next point of 1,050, 150, we're going to have the profit to be 1.5 times 1,050 plus 2 times 150, which is equal to 1,875. Okay, and then at 600 and 0, we're going to have the profit to be 1.5 times 600 plus 2 times 0, which is equal to 900. Right? So this one is the maximum, right? The maximum profit, which is 400, which is right here. This is our maximum. So we know that we have to produce monthly 800 boxes of chocolate covered creams and 400 boxes of chocolate covered nuts, right? So our x is equal to 800, y is equal to 400, and which leads to our profit to be $2,000. All right. Perfect. So now, of course, we can also reverse it to do an optimal cost problem, right? An optimal cost problem. So for optimal cost problem, we can do it the following way. So, okay, the liquid portion of the daily diet is to provide at least 300 calories, 36 units of vitamin A, and 90 units of vitamin C. 2 dietary drinks, drink X and drink Y, will be used to meet these requirements. Information about 1 cup of each drink is shown below. how many cups of each dietary drink must be consumed each day to satisfy the daily requirements of the minimum possible cost, right? At the minimum possible cost. So essentially, we're given that. So we know. Let's write down our, well, first of all, our cost function. So it's going to be 0.72x plus 0.90y. Right, that was pretty straightforward. Okay, how about constraints? Constraints are going to be as following. So we're going to know that, let's see. So we know 300 calories, right? So in order for us to get calories, we got to have, well, 60x plus 60y, right? 60 and 60 must be greater or equal to 300 at least. Then we know that 12x plus 6y must be greater or equal to 56. And then 10x plus 50y must be greater or equal to 90. Right, and of course, we have to make sure that x is greater or equal to 0, y is greater or equal to 0. Okay, pause the video and try to find this region. Okay, so after you find this region, right, you should get something like this. This is going to be unbounded region. Okay, and we have 4 points, right? So we want to find the minimum cost, so we're going to be trying to find the minimum value. So at 0, 6, we will have c to be equal to 0.72 times 0 plus 0.9 times 6, which is going to be equal to $5.40. Okay, at 1, 4, we're going to have that the cost value is 0.72 times 1 plus 0.9 times 6, times 4, which is equal to $4.52. Okay, and then at 3, 2, we're going to have that the cost is equal to 0.72 times 3 plus 0.9 times 4, which is equal to 3.96. Okay, and then the last point is at 9, 0, which is equal to cost is equal to 0.72 times 9 plus 0.9 times 0, which is equal to 6.48. So clearly, this one is a minimum at a point 3, 2. Right, so 3, 2 is going to be our minimum. Okay, perfect. So now we were able to actually solve this. Okay, perfect. So now, that's essentially would be it for all of the linear programming stuff. So next time we're going to move on to series and sequences of algebraic expressions. And well, here is an extra problem for you to solve. You can try to solve this problem on your own, and it's going to be similar to the cost saving. All right, thank you, students, and see you next time.